died.
I just want to make sure that
I'm just preparing the.
Yeah, I already.
I go. Super. Thank you. So, last time, with your quick recap on gauge tree theory, where I presented the kinematics as the geometric objects. Geometry, basically, and the dynamics was given by Lagrangian. An action, functional, and I just wanted quickly to finish before proceeding further to give a very, very quick recap on simply not a charge or not a term, not the charges in gauge field theory, because again, in the context of gravity, the use of Cartan geometry give a nice result there, something meaningful. So the idea, of course, of Noether theorem is that variational symmetries of the action. So Noether theorem, basically, variational symmetry of the action functional correspond to conserved. Correspond to conserved currents, conserved charges, conserved quantities in general. So, symmetry, of course, it is something very important in physics to find conserved charges that are physically interpretable, by the way. So, how does this appear within the framework that we have presented last time? So, in the case at hand, the symmetry that we have is the gauge symmetry. So, for example, so since L is H invariant, so I remind you H is my notation for the gauge group of the bundle P. So isomorphic to the automorphisms, vector automorphisms. The question is, what are the associated charges to the gauge group? And so, for chi, an element of the Lie algebra of the gauge group, so we will say it is an infinitesimal gauge transformation. We will say that we note delta chi like this. Yes. So the infinite gauge transformation of something, a field, a functional of the field will be not like this, and so the point is that we will have this by construction of the action of the Lagrangian, right? And same for Lagrangian. And the variation of the Lagrangian, you remember, we have a variational principle that gave us, basically, we had the variation of the Lagrangian that gave us field equation plus a boundary term that we call the presymplectic potential. Like this, right? So we may be. So for variation that comes from the symmetry, we will have delta KL equal the same thing plus the theta, delta K phi or phi, like this. But this is supposed to be identically zero. So identically zero by symmetry of the Lagrangian. And it means that when you are on shell, so on shell is the terminology of physicists to say, well, we are on the field equation, where the field equation holds. Then you see that we have something that is conserved, a quantity there that is a conserved quantity, and we will call that the Noether current. notor current, which is linear in the gauge parameter, in the chi, and depends functionally in a non-detailed way on the field, and it is by definition theta phi. So it is declosed, and the notor charge that we after. Therefore, so this is an, you can see, given this, this is an n minus 1 form on M on the base space. So it is a current n minus 1 form on M. So given a collimation 1, submanifold sigma on the base space, we define the notor. So we define the notor charge as being, so depending a priori on the surface, even though we can show that that shows that it's not relevant, but like this, which is simply the integral, and this is a conserved quantity that we may try to interpret, and it's happened that on shell, so using the notation of the physicists, some physicists, to notice the on shell situation, it is possible to show that in the end this reduced to a boundary term. Right. So the notor charge for a gauge symmetry is a boundary term, and this is called a quasi-local because of this. Like this even. This has been come to call a quasi-local charge. Quasi-local charge because it is associated to the whole region and not to a point. Right. Very good. And so just to give the example of what this looks like in one specific case. So if you look at Young-Mills theory, so we remember that the Lagrangian was given by something like this, where F is the curvature, field strength of the Young-Mills potential, the curvature of the connection, and we had the field equation, so delta A, delta L, Young-Mills, this was d theta delta A, and we have that this, remember, was given by this, right? So when E equals 0, we have the Young-Mills equation, d star F equals 0 plus, and the boundary term that we obtain by integration by parts is simply this guy, so that in the end, the Young-Mills charge in that case is, sorry, the integral of the sigma of the trace of chi, trace of, so yes, in this case, of course, the infinitesimal gauge transformation of the connection, the Lie derivative along vertical vector fields of the connection is simply given by the covariant derivative of the parameter, which is a tensorial zero form, so that makes sense. So we have this, and it is quite easy to show. We integrate by part. We again reproduce in this integration by part the field equation, the only field equation, and therefore we show that using again d star F equals 0, we would get that it is simple boundary term given by trace of chi star F. Okay. So again, this is assuming the field equation here. So this is a boundary term, and massaging a little bit this turn, this is the electric charge. Okay, in the Young's case, in the Maxwell case, the abelian case, this will give the electric charge. For example, in the region, this is Gauss law, basically. It gives you back the Gauss law. That term. Okay. So I introduced this just to show that, okay, now looking at gravity, situation will be a little more complicated, but treatable nonetheless. So that's all I wanted to say as a reminder about gauge field theory. Now I proceed with gravity. As I told you before, so the last time, we are interested into gauge theories of gravity. The motivation being that, okay, the three other, yes?
It's not really electric charge though, right? It's only electric charge for like constant
yeah,
gauge,
absolutely. If you now assume that K is a so-called rigid gauge transformation, it goes through the integral, it goes out, and then you have the integral of this. This is electric flux, basically.
But then it's not really something associated to gauge symmetry per se.
No, indeed, that's why I said this is a little bit of massaging and approximation, or you can also do as go back and say, okay, let me imagine that A is the sum of a background configuration plus a fluctuation. So you take advantage of the affine structure of connection space, and you say, okay, I have a background configuration was killing symmetries, right? And chi being one of those killing symmetries. And so in the end, at least formally, you reproduce something which is, in the abelian case, exactly the flux of electric field through the boundary. And you know this gives you, by the field equation, this should give you the electric charge or the electric current through the...
But then, like, calling that thing upstairs nether charge, that's confusing in it, like, for gauge symmetry.
Yeah, that's the use in some part of the community, to call them not a current, not a charge. I define like this. Yeah. But I know that this is, yeah, you might want to distinguish the first and second method theorem, one for the rigid, one for the rational width function, I agree, but okay. That in part of the community, doing that kind of stuff, which is called covariant phase space approach to stuff, people use this terminology without leaving too much of a...
I think usually for gauge symmetry, the Noether charge is a codimension 2 object.
Indeed. On shell. Yeah.
Codimension 2.
Well, yes. Sigma is codimension 1, so the boundary of sigma is codimension 2. So, yeah. Indeed. Yeah, totally. You agree that on shell, the Noether charge for the gauge symmetry will be a boundary term on shell. Yeah. That's true. Yes. And so now the rationale that motivates to find a gauge theory of gravity. We already know GR. We know the metric formation of GR. While there are several motivations, one of them is that maybe by having a gauge formulation of it, we may have better path to its quantization. Maybe we have a better opportunity to unify it with the other three non-directional interactions. And anyway, you are compelled, so to speak, to do it if you want to treat the coupling of gravity to fermionic matter, right, to spinors. So, and I agree that indeed it turns out that Cartan geometry is the right framework to do that, I would argue. So, just a little background to understand how this developed historically, again, to give you a bit of the physical background. So, historical backgrounds, like this. So in 25, Einstein introduced the local SO1, the local SO13, and then in 1929 it was by again use it plus the tetrad field to couple to local SL2C, two-coupled matter to fermion. So again, motivated by this. In 1955, a physicist that is not very well known, unfortunately, Ryoyu Uchiyama, Japanese physicist, discovered the formal gauge, so the general structure of gauge field theory, meaning that taking any Lie groups, he understood how to build the associated gauge field theory, not knowing, of course, the differential geometry developed by mathematicians. Yes?
Sorry, that says SL2C directs on what?
Sorry?
With Weil's contribution, it's
Sorry, plus, no. And the tetrad field. So it's not...
and what? What's the second word?
Tetrad field, sorry.
Tetrad.
Oh, tetrad.
Tetrad. Tetrad field, yes. Einstein already introduced it here, of course, but in the case of Weil, it was indispensable to couple with fermions, basically. So Uchiyama discovered the general structure of gauge field theory for any groups, and unfortunately for him, the theory is known by the term Young-Mills. Because Young and Mills find it for SU2. Okay, so they are priority. And of course in the 70s, I cannot give a precise date because it's a flurry of many variants of gauge field theory of gravity. For example, Poincaré gravity, or affine gravity. Affine gravity, we have also conformal gravity. We have conformal gravity, Maxwell-Mansouri. All different atoms, and of course we have the in the same period we have twisters. The twister approach of Penrose to gravity and other things, but all those in the end has to do with the gauge structure of gravity. But there have been quite a lot of confusion, I would say, approaching things only from a gauge field theoretic perspective without knowing the proper geometry, probably. One issue that arose was a frequent issue. It was, for example, some degree of confusion, I would say. Subject, for example, the gauging of translation, which doesn't make much sense from a physical point of view, but seems to be something that came naturally in, for example, in Poincaré or affine gravity. And people doing that were trying to identify the gauge translation with diffeomorphism, so to go around this technical issue, this seeming redundancy of having both diffeomorphism of the base manifold and some kind of internal gauge translation that doesn't have a natural place in gravity theories. Another issue that I will very quickly mention relating to nutter charge is that the definition of mass and angular momentum has been quite a challenging issue in gravity theories, especially the metric formulation. There have been various attempts. Arnold Deezer, Missner decomposition, or King Penrose propose a notion of quasi-local mass, right, at finite distance. Even recently, I think Yao, the guy from Galileo, the mathematician, did propose a definition of mass and angular momentum in metric GR to get a finite and well-defined notion of mass. So it's not entirely trivial. And I would argue that from Cartan geometry, in some situation, we have a well-defined asymptotic notion of charge. I will try to show this, convince you of this. So let's go into the main thing, Cartan geometry. Brief recap. course, we have already seen a lot the basic definition, so maybe I can be quicker than I intended to be. So but let me at least give you the definition as I understand it, which is not very different, but the Cartan geometry will be a pair, so this is var pi, right, or omega with a bar to distinguish for Riemann connection. So P, where P is a H bundle over manifold M, and omega, sorry, var pi, is an equivariant one form on P with value in Lig, where Lig contain Lich. So of course this is what mathematicians among you will call G and P, for example, in the parabolic case. But as Jan said, for now I don't assume anything apart from the fact that it is a group or subgroup for now. So it satisfies the three defining property. First, of course, equivariancy means that we have this. It is a projector on vertical vector fields. So xv equals x in h for x v, a section of vertical.
The project is correct and H, right? Not G.
Sorry? Yeah, sorry. Thank you. And the third, of course, is that the Cartan connection is a linear isomorphism between the tangent space at any point and Lig, or an absolute parallelism. And so those are the same as for an Riemann connection, as you will know. And that third defining property is the one that's from which flows a lot of nice specificities of Cartan geometry, all having very, how can I say, making Cartan geometry the right framework for gravity. Because essentially, what that one means in particular is that, let me say it like this. So that I'm used to say to my colleague that this last property implies that P encodes the geometry of M, right? And by the way, we heard that Einstein says gravity is the geometry of M, essentially. So both together, so admitting that this will hold true in all classical theories of gravity, we have that Cartan geometry seems perfectly fit to be the geometric foundation to give the kinematics of any gauge field theory of gravity, basically. So what is nice? What is nice in this framework, of course, or the first thing, for example, so to A, gauge symmetry. So here, very simple. The gauge symmetry, of course, is still the one of the bundle P. So it is the vertical automaton of P that is the gauge group here. And so in particular, this means that we will avoid those kind of situations. We'll see in an example, but for example, no gauge translation. Because in the 70s, physicists were used to treat gravity as they treat other interaction. And when they looked at an object with value in some Lie algebra, they are used to identify the symmetry algebra with the thing in which the gauge potential was valued in. So looking at Poincare gravity, for example, you would have Lorentz times semi-direct to translation, and therefore you say, okay, sure, so we have local Lorentz, and we also have local gauge translation. This cannot happen, or do not naturally happen, in Cartan geometry. So we immediately avoid that kind of confusion. Most importantly, as we know, this implies a soldering, right? A soldering, meaning that we have, by the three axiom, it is possible to show that essentially it means that vector fields are encoded as 0 form of P in the H. So again, showing how, in a sense, P will indeed encode the relevant geometry for gravity, right? In some sense. To say it otherwise, or so said otherwise.
Sorry, what is the subscript?
Sorry?
Next to the omega?
Sorry. I'm a bit quick. Tensor, so it is horizontal, well, zero form of course, but equivalent zero form. So say otherwise, consider. Yeah. So let's just consider the projection of Lig to the quotients here. Lig into Lig H, right? So if you look at this, we can define the soldering form as being, let me call it theta, as being tau of omega, and this will be by definition a tensorial form on P with value in this. Well, because of this, it will be obviously horizontal, and it keeps its equivalence, so it is still well defined. And locally, in particular, so yeah, sorry. Yes. So we look at this locally, because indeed, when you do physics, you do everything down on the base manifold, right? On an open patch. So locally, if I take a local section like this, I will define locally. I will define A as the pullback of my Cartan connection, and E will be defined as the pullback of theta, like this. And so in a coordinate system, x mu on mu, we will have E equal EA plus EA mu dx mu, and this object is what? Tetrad field, what we call in physics the tetrad field, the Villebine, Villebine in 4 dimensions, Villebine in many dimensions.
Can you repeat what was the soldering form above?
So it will be defined like this.
But what is in the parentheses?
That guy here.
Theta
I think it's on.
but
It's omega bar.
Omega bar. And then
Because
here is tau of omega bar, the Cartan connection. Right, so yeah, so the Cartan connection is my omega bar, sorry for my poor calligraphic ability. And so it's just the Lig part of the Cartan connection. Right? And yeah. So if I look at all my global objects locally, through local section, this will be the local representative of my Cartan connection, and this will be the local representative of the soldering piece of this piece. And in a given coordinate system, it will have these expression, and this is what physicists usually call the tetrad field of the Villebine. Yeah. And this object will induce a metric. So induce metric. It can induce a metric on N. So if there exists a bilinear form on, so bilinear form, let me call it eta on Lig H then Lig H into R, of course non-degenerate, non-degenerate linear stuff. Then you can define G as being eta E, like this. Right? So y will be G xy equals eta E x E y. And again, in coordinates, this is nothing but the very well known formula that we find in every textbook in GR, advanced textbook in GR, that express the metric field in terms of the solar ring of the tetrad. So it's very nice to see this coming naturally from the Cartan connection. And of course, if eta is in H invariant, this will be well defined across. This will be independent of the local section used to define E, and so this will give us a well-defined metric across all the manifold. If it is invariant on only up to a scalar positive function, this will define a conformal class of metric on the base manifold. And this is what happened in Cartan conformal geometry. The Cartan connection can induce a conformal class by the action of the gauge group on the Cartan connection, on the soldering part of the Cartan connection. So that's very nice to see a relevant object for gravity encoded in the Cartan connection in an obvious manner, giving us.
So what are you putting down as G now? So yeah, what's your G? You haven't mentioned what G is as a group.
Yeah, so that guy.
No, big G. The group G.
The group G.
Because you're talking about conformal now, so.
Yeah, indeed, I didn't. I just started with the lead G. That's
yeah.
Indeed,
so are you going to pin down what you mean by G? Or?
Well, in this case, in the conformal Cartan, G would be SO24, in 4-dimensional SO24, for example. And H would be the parabolic subgroup of the thing.
Yeah.
And the action of the parabolic subgroup as a vine rescaling parts that would act on E.
Sure. Yeah, okay. But that's what we're thinking of at the moment.
Yeah.
Okay.
And so, of course, this has one good thing is like now, again, given an H invariant or well-defined stuff, well-defined metric, you can define urge. You can define an urge operation on M, and this is indeed the ingredient we needed anyway, even in Young-Mills theory. Right? So it's very good to have it appearing given for free once you have a Cartan connection. So to speak. One remark that may be interesting is that to some degree, you could say that E is the formal implementation or counterpart of the equivalence principle. Because basically it says that okay, on the manifold you can always find a coordinate system such that the metric can be put in a Minkowskian diagonal shape, so that any spacetime is locally Minkowski, so to speak. So in a sense, the fact that this object exists is a formal implementation of the equivalence principle, which is also used for many people, is still a key physical insight typical to gravity that doesn't exist, that doesn't have a counterpart for the other interaction. Very good. So, given all this, one takeaway is that I didn't say it there, but okay. I should say that. So, given this, you could say that within this framework, the local representative of the Cartan connection, or the Cartan connection itself, is the generalized gravitational potential. So in the same way that in Yang-Mills theory, the connection was the Yang-Mills potential, then the Cartan connection is the gravitational potential. Or in code, the gravitational degrees of freedom. So, now I guess I just wanted to give, perhaps in the few minutes left, a word about Cartan curvature, because of course this would be an important piece in the geometry.
To which extent the terminology is applicable? So you'd like to just have this G mu, or you'd like that to be H equivariant? So can you specify?
Sorry, excuse me, I didn't-
When do you apply the gravitational calculation? When you have this eta to be H equivariant, or in general?
Sorry, I didn't get
You have eta, right? In this case, you talk
eta.
about
Eta, yes,
yeah. But
yeah.
you want it to be H equivalent or completely general?
No, I would like to be H equivalent.
It's form.
Yeah, eta. Well,
You claim it to be H equivalent or not?
yeah, probably better to be, but in the case of conformality, it will not be, for example. Equivalent, yes. Yes, equivalent it must be. Invariant, not always. Equivalent, yes.
So when do you talk about gravitational potential? In all cases or when it's H equivalent?
I would say in maybe not in all cases, but in all cases where the geometry gives a reasonable physical model.
Sorry, I don't know what that means.
But what I mean is that when you apply the formalism to, I will give a series of examples, for example, of classical theories of gravity. And in all of them, either the eta will be invariant, or like in conformal geometry, it will be equivalent, meaning even up to scalar functions.
So it may be conformal gravity.
Yeah, exactly. Yeah. So, so just quickly, Cartan curvature. So, Cartan curvature. So of course, Cartan curvature will denote like this. It is given by Cartan structure equation. It is a tensorial two form on P with value in Eg. And again, given the projection that we define there, we can define the torsion, right, as the Lie, Eg, EH piece. So this would be the torsion of the Cartan connection. Again, this is something that obviously doesn't exist for in gauge field, in Yang-Mills type gauge field theory, right? It would be trivial. And the Bianchi identity gives us immediately the Ricci identities, differential and algebraic Ricci identities that is used often in GR. And so, the point is that so F, which would be the local representative of the curvature, would be the generalized gravitational field strength. Okay. In the same way that the curvature of the Reichmann connection gives us the Yang-Mills field strength. Gravitational field strength. So I say generalized because indeed usually the depending on who you ask, but the torsion is considered or not part of it. But the Cartan curvature contain both. And finally, another, I'm trying to parallel the dictionary that I've given at the very beginning of the lecture for physics and mathematics. And so finally I have the covariant derivative that is given also for tractor connection. So on account of the first two axiom defining properties of the connection, so as usual, given the representation rho v of the structure group, right, we can build associated bundle like this, and if furthermore we have that v is also a Lie module or representation with rho star Lie into GLV, for example, or let's me yes, rep like this, then we can define, so again on account of 1 and 2, given 1 and 2, we can define D plus rho, which will give you a covariant derivative on the space of section of that guy, or generally on the space of tensor form. Right, so in the same way that the RH1 connection gives us naturally a covariant derivative on the section of associated bundle, this is also the case for the Cartan connection, at least from the, and this will be the minimal coupling. This will give us the minimal coupling of gravity with matter field, like it was in Young state. Indeed, so I should write it. So please, minimal coupling to gravity. Again, on account of the fact that we have said that the Cartan connection is the gravitational potential. So this object will give us, or the local representative of this object, of course locally, we'll have something like D plus rho star of A, right? Something like this. Very fine. And in particular, so now I would probably say things that are even more outrageous to some of you. So in particular, so if so supposing that Lie G comes from a group G, rep of G, like this, and so rep of H by restriction. Okay. In general, you will call T P B the tractor bundle. I think this is a general definition given in the book by Jan and Andy. Tractor bundle given like this. So it's a case of associated bundle. And yeah, and then the restriction, and so D on tractor connection. And so for example, to connect with the torque of rod, for example, in conformal geometry, you can of course build a guy like this on the defining representation of SO24, for example, and the Cartan connection, or the normal Cartan connection, will give you the canonical tractor, conformal tractor connection on the tractor, the standard tractor bundle built with the standard, the defining representation of SO24. Right. And it turns out that this object is exactly the nice object that should appear in conformal gravity. Right. And in okay, yes. Yes, very good. And in particular, if those are spin representation, for example, or spin covering, we will have the section will be spinors for those groups, and therefore we'll have the minimal coupling of gravity to matter field to spinors. So this gives us naturally, for example, in some specific example, this will give us the Dirac operator.
And so what do you actually mean by minimum coupling? Minimum coupling to what?
Well, again, that's the terminology of physicists to say how you write concretely the coupling of matter fields through with the fields that mediate the interaction. So in Yang-Mills theory, you had something like this. D of some field. Let me take some fermion already. So fermion, charge fermion, for example, in Maxwell, you will have something like this. And this is a minimal coupling term because in the Lagrangian of Maxwell, for example, you would have terms and this piece, so you have something like, if you write a Dirac type Lagrangian, you have a piece which is like this, approximately, and this contains a piece which is psi, a psi, and this piece tells you that the matter fields interact by the exchange of the mediating fields, the photon, for example, in that case. And yes, and so this is called the minimal coupling because it's the simplest coupling you can imagine in a theory polynomially. No?
So it's more intuitive notion than referring to some kind of minimality in the.
Yeah, I don't know where the minimal adjective comes, but I assume it comes from the fact that it is the simplest possible coupling you can imagine because it's really it is really a. If you look at the quantum theory, the quantization of that stuff, what you get is a Feynman diagram with its only with a 3-point interaction, with the very simplest possible, non-trivial that you can have. So you could have an electron, for example. So this is time evolution, for example. Okay, so space, time. So you have an electron arriving, he emits a photon and goes back. Simple as that. Or it can be something like another, like this. Like this. So again, two electrons incoming, feeding one another, exchanging a photon, and then separate. So that's the electrostatic propulsion, for example, look like this, and it is entirely accounted for with theory by a term like this. So this is very simple, study.
So if you were making a Lagrangian, what would be a non-minimal coupling?
I guess something more. In higher spin theory, I think, if I'm not wrong, I think they propose some more higher polynomial concatenation of fields. That's what, something which is. But to my knowledge, there is nowhere in physics any of those stuff. In fundamental physics, none of those higher polynomials coupling give anything meaningful or experimentally validated. Yeah. Wow, super good. And well, I guess I'm perfect. I think I will end here and give you in the last 50 minutes just give you the explicit Lagrangian and example of application of this, and show in particular how charges can be well defined when you choose the geometry adequately. So thank you very much.
Questions, comments, remarks?
I think in the physics textbooks that minimal coupling usually refer to a procedure where physicists think of a theory without matter, and then they are wondering how could we couple matter to this, and then they are replacing partial derivative with covariant derivatives. They're replacing partial derivatives with covariant derivatives.
Yes, yeah, they apply the gauge principle indeed, but the point is that this kind of coupling were known before. You know, it was already written in the theory, and it's just that by applying the symmetry principle, you would have kind of a heuristic to arrive at such in a motivated way at such a form. But I'm still I still don't know historically where does the terminology come. Why is it called minimal coupling? I think, well, it seems clear that it is, for reason of simplicity, the minimal modification possible to the free Lagrangian to get an interaction theory. Basically.
So maybe, are you familiar with the work of Westman and Zlotny?
No.
So, because I'm quite curious for the next lecture, and they also consider this kind of Cartan approach to gravity.
Okay.
And so maybe we can discuss tomorrow after the lecture. And the second question, if I may, so just a short one. So how much this is dependent on the dimension? So if you go to, for example, if you would like to describe like, I don't know, 5, 6, 7, whatever dimensional gravity, stuff like that, how much this is dependent on the...
Good question. Actually, I would say the kinematics doesn't depend on it depends on the, when you want to build the Lagrangian, then you would have to use the polynomial. You know, again, when you write the physics, the dynamics, you have to choose the Lagrangian. So you need a, you need a pairing, you need a polynomial on the Lie algebra and stuff. And for example, the kind of polynomial we use will depend. For example, in even dimensional gravity, you can use the epsilon, for example, which will be parity invariance. In odd dimension, you will have something. If you use that one, you will have something which is not parity invariant. So
and you are also dependent on the fact that you can split nicely the tetrad from the rest, right? So what happens in the case if this is not possible?
Yeah, indeed. Well, in that case, yes. I wanted to start the next lecture by saying, okay, we restrict our discussion to the case where reductive geometry or even parabolic geometry, where you can have such a nice splitting, because indeed you would have you want this clean splitting, at least for realistic models of gravity. So
you want splitting.
You want it, yeah.
Can your groups be supergroups?
Good. I want to not finish the next talk by addressing that question precisely, saying that admitting that what physical bosonic or classical gravity field is well described by standard Cartan geometry, you would expect that supergravity should be accommodated within a super Cartan geometry, which is something I'm working on. And at least for model of supergravity, where the gauge potential is a one form, super one form, or one form is the value in a supergroup. Yes, that would super Cartan geometry with a supergroup we should be able to accommodate.
And to Cartan geometry, the supergravity without passing to the super cage.
Oh, probably, but I would argue that it's the
so the super cage is not necessarily always.
No, sure, I agree. It's just aesthetically, I think a super Cartan geometry would be the most natural thing to do.
I'm not sure.
Okay, we can agree to disagree.
I propose to.
Yeah. Yeah.
Okay, I propose to move discussions
absolutely.
supervision to the coffee and thanks to the speaker again.